This is the review for our upcoming test on three-dimensional geometry. Problem 1 is a problem from an SAT test preparation resource. It says 27 white cubes of the same size are put together to form a larger cube. The larger cube is painted blue. It's a quantitative comparison problem, so we're comparing the quantity in this box, box A, to the quantity in box B. The quantity in box B is 9. The quantity in box A would be the number of smaller cubes that have exactly 3 blue faces after we paint the large cube. So we need to draw a picture to be able to visualize this large cube. If I have 27 white cubes, you may know right away the dimensions of the larger cube, but if you don't, drawing a picture will certainly help. Okay, the volume is area of the base multiplied by the height. In the case of a cube, all of the sides are congruent. The area of the base would just be side times side, and the height is the same length as the side also, so it's just s cubed equals 27 in this case. And so if you understand what number cubed gives you 27, you'll realize that the side length of this cube is made up of 3 of the smaller cubes. 3 times 3 is 9, and 9 times 3 is 27. So if you were to visualize the individual cubes that made up this larger cube, it would look like this. If I drew it better, and these would go back this way. It's basically just understanding that it's a 3 by 3 by 3 cube. Of course, we'd have it on the top too. I'm not going to spend, I should spend at least enough time to make sure that this is, I don't like the videos to be overly long, but also want to be clear, so that's the balance I'm trying to strike here. Okay, we'll go with that. Okay, so these are the 27 individual white cubes, and then the whole thing is painted blue. The number of smaller cubes that have exactly 3 blue faces, you have to think about the different positions for these smaller cubes. The cubes that are in this center position will definitely not have 3 blue faces when it's dipped in blue paint, because only one face is exposed. These cubes that are on the edges here would have 2 blue faces like this, but the cubes that are in the corners, like this cube right here, you can see that it will have 1, 2, 3 blue faces. This cube will also have 1, 2, 3, the one that we can't see underneath, 3 blue faces. So once you realize it's the corner cubes that have 3 blue faces, you have to think about how many corner cubes are there. It's the same number of corner cubes as you have vertices on this large cube. There are 1, 2, 3, 4, 5, 6, 7, 8. So the quantity in box A is 8. And that's less than 9, so B is greater than A. Problem number 2 asks you to find the measure of an interior and exterior angle of a regular pentagon, hexagon, 25gon, and 100gon. We're going to just focus on the pentagon and then extend our understanding of the pentagon to these other shapes. So I'm going to do my best to draw a regular pentagon here. Okay. This is an interior angle. An exterior angle would be the angle that is adjacent and supplementary to the interior angle. So let me try to do my best to draw an exterior angle here. Oops, I didn't want that to be. Okay, that's an exterior angle. So I'll use E for exterior and I for interior. There's different ways to get these angles, but one thing we did in class was pick a vertex on the figure and draw all the diagonals from that vertex. So if I draw these two diagonals, I see that my regular pentagon can be divided up into 1, 2, 3 triangles. We know each triangle has the sum of the measures of the angles of a triangle are 180. So I have 3 multiplied by 180, or a total of 540 degrees in my whole pentagon, all 5 angles altogether. So then I can do 540 divided by 5 to determine that each interior angle is 108 degrees. So the interior angle equals 108. We said the exterior angle was adjacent and supplementary. So the exterior and interior angle have to add up to 180. So if we do 180 minus 108, we get 72 degrees for the exterior angle. Now, we could do this for the hexagon. When we start to try to do it for the 25 gon, we're not going to want to have to draw these figures. So there's one other relationship that I want to remind you of. First, let's circle our answer for the pentagon. We learned that, let me try to draw them in just for this one figure. If I draw all of the exterior angles, I feel like I missed something. I just wasn't consistent. That one should really be drawn here. I mean, it could be drawn in either place, but if I want to fit them all on there, I really need to be consistent in the way I'm doing this. So there are 1, 2, 3, 4, 5 exterior angles, and each one of them is 72 degrees. Well, if you do 72 multiplied by 5, you get 360 degrees, which is the number of degrees in a circle. And this will always be true for any polygon. The sum of the measures of all the exterior angles will equal 360. So we can start to use that on these other problems to work backwards. In other words, for the hexagon, it will have 6 exterior angles. So 360 divided by 6 equals 60 degrees. And so the exterior angle equals 60 degrees. The interior angle is supplementary, so it must be 120 degrees. And you can double check that by dividing the hexagon into 4 triangles by drawing diagonals from a single vertex, as we did here. 4 times 180 is 720, and 720 divided by 6 is 120. So that's just a way of checking, but you can count on that if you take 360 divided by the number of exterior angles, you'll get the measurement of the exterior angle. So we'll do this for the 25 gon. 360 divided by 25. I don't know that off the top of my head, so I'm going to just do that division real quick. There's 125 and 36. Subtract, I get a difference of 11. Bring down the 0. There are 4 25s and 110. And bring down the 0. I'm going to get exactly 4 25s and 100. So the exterior angle for the 25 gon is 14 and 4/10 degrees. And the interior angle would be 180 minus 14 and 4/10. $165 and 6/10. I'm just going to quickly add those back together. 179, 180. Yeah, that's right. So for the 25 gon, these would be the measurements of the exterior and interior angles. For the 100 gon, it's actually a little easier because it's easy to divide by 100. I just move my decimal 2 places to the left. So the exterior angle equals 3.6 degrees, and the interior angle would equal, what would I add to 3.6 to get 180? I would add 170, not 7, because then I'd be over, 176 and 4/10 degrees. Okay, that completes problem 2. Problem 3, sketch the top, front, and side views for the figure. The orientation has been provided. We're saying that this is the front, so if I'm drawing the front view, I'm looking from there. If I'm actually make something clear, although this figure is so symmetric it probably wouldn't matter, but you imagine you're standing at the front and looking down. That will be our top view. So when I draw the top view, I imagine I'm standing at the front and looking down at the figure. I would see a 3x3 square. The front view, again, I'm standing at the front, I'm looking directly at the figure. I would see this row of 3 on the bottom, and then I would see another row of 3 above it. Even though this cube is set back, it would still be part of this row of 3. The side view would look identical to the front view. So you sketch the same thing, and that's what it looks like from the side. Problem number 4, we're finding the volume of this solid. First thing we need to do is identify what are we looking at here. If this thing is sitting on a table, it's sitting on this rectangular face, but that is not the base. You have to look and decide whether this polyhedron is a prism or a pyramid. Pyramid has one base, prism has 2 bases. This polyhedron has 2 bases. They happen to be this triangle and this triangle, because those 2 triangles are congruent and they're parallel. If you were standing this object up on the triangle, then you can sort of visualize better that 2 triangular bases that are parallel and congruent. The formula for volume of a, in this case, triangular prism, or any prism or cylinder, is area of the base multiplied by the height. Then we use the formula for area of the base shape depending on what the shape is. In this case it's a triangle, so the formula for area of a triangle is 1/2 base times height. So that would be 1/2 multiplied by 24 multiplied by 8, which is 12 times 8, which is 96. Then we can substitute the area of the base into the volume formula. Volume equals area of the base, so 96 multiplied by the height of the prism. This is the other thing I want to emphasize. The height of the prism is the perpendicular distance between the parallel bases. So this is not the height we're talking about. We're talking about if I stood this thing on its triangular base, either one of them, how tall would it be? Well, the distance between these 2 triangular bases is the 16 meter dimension. And so it's 96 multiplied by 16. I'm going to do this quickly by thinking of 100 16s as 1600, but I wanted 96 16s, so I want 4 16s less than this. 4 16s is 64, so I'm going to subtract 64 from this, which I can do mental math because I just think, what would I add to 64 to get 100? That's 36, so 15. 36. The units will be meters cubed because volume is 3-dimensional. It means how many 1 by 1 by 1 meter cubes could I fit inside of this three-dimensional space. So 1,536 meters cubed. That completes page 1. We'll continue the review with page 2 on the next video. Thanks for watching.